The problem we have is no longer seeing space. It's making sense of what we've already captured. There's not too little to observe, but too much. And most of it lies beyond what our eyes can detect. Today, artificial intelligence is giving us a new way to see, not by replacing telescopes, but by helping us to interpret what they capture. When we look at the night sky, we see visible light. But most of the universe doesn't emit light in wavelengths that our eyes can detect. Radio waves, infrared radiation, X-rays. To study the universe, instruments like the James Webb Space Telescope and the Hubble Space Telescope collect data across these invisible spectra. What they produce isn't a photograph in the conventional sense. It's data, vast, complex, and often incomplete. In astronomy, the signal is often faint, partial, and buried in noise. AI systems are trained to recognize those signals, even when they're incomplete. Machine learning is allowing us to detect structure in the data that would otherwise appear random or insignificant. For example, AI is now used to identify distant galaxies in deep field images, extending the reach of what we can reliably detect. Consider how we detect planets around other stars, exoplanets. These planets are too distant and too dim to image directly. So instead, astronomers observe the brightness of a star over time. When a planet passes the star, it causes a minute dip in brightness. This is known as the transit method. The change is extremely subtle, often less than 1%, and can be obscured by noise, instrument drift, or stellar activity. Missions like the Kepler Space Telescope have produced light curves for hundreds of thousands of stars. Each one is a long, fluctuating signal. AI systems have been trained to scan these light curves and identify the specific pattern of a planetary transit, distinguishing it from random variation. This has led to the discovery of exoplanets that were already present in the data, but just not previously recognized. AI is not only finding these signals, it is also helping to reconstruct them. In radio astronomy, telescopes like the Square Kilometre Array collect fragmented data across large distances. AI techniques combine these fragments, reduce unwanted noise, and produce usable images. This allows us to resolve structures that would otherwise remain indistinct. One of the more significant shifts is that AI is not just accelerating discovery. It is changing how discovery even happens. Traditionally, astronomers defined what they were looking for and then searched for it. Now, AI systems can scan datasets without predefined categories, identifying anomalies, signals that do not match known patterns. In effect, AI allows us to notice what we weren't thinking to look for. But there's an important distinction. AI does not understand space. It identifies patterns. Human interpretation remains essential. AI can reduce the complexity, but it doesn't replace human judgment. These systems are not without limitations. They depend on the data they're trained on, which may be incomplete. A false signal can appear convincing, especially after reconstruction. For this reason, AI-supported findings require independent verification. Certainty still takes time. Space has not become more visible, but our ability to extract meaning from it has improved. From a faint dip in starlight, we can now infer the presence of a planet. We are learning to detect what was always there, but never directly visible. The universe is full of signals we can't see. But space is only half the story. The same techniques that are revealing hidden patterns in distant galaxies are now being used to detect subtle changes on our own planet. In Part 2, we turn from the cosmos to Earth and explore how AI is making environmental change legible long before it becomes visible. Click subscribe to be notified of the next installment, and thank you for watching.